Watch closely. A gecko is running straight up a pane of glass. No claws digging in, no sticky glue, no suction. The surface is smooth, vertical, and, to almost every other animal on Earth, completely impossible. And yet the gecko moves across it the way you'd walk across a floor. It can even hang from that glass by a single toe, holding its entire body weight against gravity, and then let go and sprint away a fraction of a second later. For decades, this was one of the quietest mysteries in all of biology. How does it hold on? And just as strangely, how does it ever let go? This is designed to survive. And this is the grip that took science 2,000 years to explain. People had been watching geckos climb since the time of Aristotle. Everyone could see what was happening. Nobody could explain it. The early guesses all sounded reasonable, and all of them were wrong. It wasn't tiny suction cups. Geckos cling just fine in a vacuum, where suction can't exist. It wasn't glue. A gecko leaves no residue, and its feet are always dry. It wasn't friction, and it wasn't hooking onto texture, because a gecko sticks to polished glass, one of the smoothest surfaces we can make. The answer wasn't hiding in the foot you can see. It was hiding in a foot too small to see at all. Look at a gecko's toe under a microscope, and it begins to blur into rows of fine ridges. Zoom in further, and those ridges dissolve into a forest. Each toe is carpeted with millions of microscopic hairs called setae, thinner than a human hair, packed in unimaginable density. But the setae are not the end of the story. Zoom in one more time, and the tip of every single hair splits, again and again, into hundreds of even smaller structures called spatulae. Each spatula is about 200 nanometers across. That's close to the wavelength of visible light itself. On the feet of one Tokai gecko, there are somewhere around 1 billion of these tips. 1 billion points of contact. On 4 feet. And here is where the mystery finally breaks open. Those billion tips aren't gripping the surface. They're getting close to it. Impossibly, intimately close. Close enough to summon a force that governs the entire molecular world, but one you have never felt in your life. The van der Waals force. Every atom in every material has a cloud of electrons that flickers and shifts. For the briefest instant, that flicker creates a faint imbalance of charge and a faint attraction to the atoms next to it. On the scale of a single molecule, this pull is almost nothing. It's the weakest bond in chemistry. But the gecko doesn't use one. It uses 1 billion, all at once, each spatula pressed so near the surface that the force can take hold. Add up 1 billion whispers, and you get a shout. Enough, in theory, for a gecko to hang the weight of a small child from the hairs on its toes. But raw stickiness would be a trap. An animal glued to a wall is an animal that starves. The true genius of the gecko isn't that it can stick. It's that it can stick and unstick dozens of times a second at a dead sprint. The secret is the angle. When the gecko presses its toe down and pulls slightly backward, the spatulae flatten against the surface, and every one of them engages at once. Full grip. To release, the gecko simply peels. It rolls its toes and changes the angle of those hairs, and the instant they tip past about 30 degrees, the van der Waals contact breaks. Cleanly, instantly, with almost no effort. Grip. Release. Grip. Release. 1 billion molecular bonds forming and vanishing faster than you can blink. And because the setae are self-cleaning, shedding dirt with every step, the gecko never needs to wash its feet. It just keeps climbing. Now think about what we would give for that. For most of our history, human sticking has meant one of two things: glue, which is permanent and messy, or suction, which fails on rough surfaces and in a vacuum. The Gecko has something better than both: an adhesive that is dry, reusable, leaves no trace, works underwater and in space, and switches off the moment you change the angle. So we started to copy it. Engineers built Gecko tape, covered in microscopic pillars that mimic the setae. Some versions, made from carbon nanotubes, grip several times harder than the real foot. Robots with Gecko-inspired pads now climb vertical glass walls. Space agencies are testing Gecko grippers to catch tumbling satellites and clear orbital debris. Because in the vacuum of space, suction is useless. But van der Waals still works. We are learning to climb the way the Gecko has climbed all along. And that's the thing worth sitting with. The Gecko wasn't given a tool. It was given physics. The same faint molecular force that's quietly acting on every object around you right now, the force you will never feel, is the entire reason this animal can walk on the ceiling. It didn't invent a new law of nature. It found one we had overlooked and built 1 billion tiny hands to reach it. 2,000 years to explain. 200 nanometers wide. And it was there the whole time, running up the glass, holding on with nothing but the space between atoms. If this changed how you see something as ordinary as a gecko on a wall, then you already understand what this channel is about. Subscribe so you don't miss where we go next, because we've seen how nature learned to hold on to anything. Next time, we look at a leaf that has mastered the exact opposite. A surface so perfectly designed that nothing, not water, not dirt, not a single speck, can hold on to it at all. This is designed to survive. We'll see you in the next episode.
If this made you look at the natural world a little differently, you're exactly who this channel is for. Hit like if it changed how you see something you thought you already understood. Subscribe so you don't miss the next design nature perfected millions of years before we ever showed up. And tell me in the comments what you want broken down next. I read every one. This is designed to survive. We'll see you in the next episode.